Right now, as you watch this, invisible bullets are striking you. Not from any weapon, not from any enemy, from the cosmos itself. They pass through your body at the speed of light, through walls, through mountains, through the entire planet. You can't feel them, you can't see them, but they are there, they have always been there. We call them cosmic rays. And somewhere out in the darkness of our galaxy, something is firing them at us. Something powerful beyond imagination. For over a century, we have been hunting the source. And now we may finally be close. The year is 1912. The world is on the edge of a great war, and yet, in a small laboratory in Vienna, a 9-year-old physicist named Victor Hess is about to change our understanding of the universe forever. At the time, scientists had a mystery on their hands. When they measured electrical charge in the air, something called ionization, the readings were always slightly higher than they expected. Something was charging the atmosphere, something unseen. The common assumption was simple. It must be coming from the ground, from radioactive minerals in the Earth's crust. The logic seemed solid. If radiation came from the ground, it should get weaker the higher you went, go high enough and the readings would drop to near zero. Victor Hess decided to test this. And he did it in the most daring way possible. He got into a balloon and he flew. 7 times over the course of a year, Hess ascended into the skies above Austria. He climbed to altitudes of 5 kilometers where the air grew thin, the temperature plummeted, and each breath became a struggle. He carried 3 electroscopes, sensitive instruments designed to measure ionization, and with numb fingers and a racing heart, he watched the readings closely. The results were not what anyone expected. At 2 kilometers, the ionization dropped slightly, exactly as predicted. But then something strange happened. At 3 kilometers, it stopped dropping. At 4 kilometers, it started rising. At 5 kilometers, the readings were double what they were on the ground. The radiation wasn't coming from the Earth. It was coming from above. Hess published his findings in 1912. The scientific world was skeptical. How could anything in outer space bombard the Earth with this much energy? What mechanism could possibly create it? It would take decades and the combined brilliance of scientists around the world before we truly understood what Hess had found. He called them Hohenstrahlem height radiation. We know them today as cosmic rays. In 1936, Victor Hess received the Nobel Prize in Physics for one of the most unexpected discoveries in the history of science. So what exactly are cosmic rays? The name is a little misleading. They are not actually rays. They are particles, atomic nuclei, stripped of their electrons, hurtling through space at nearly the speed of light. Mostly protons, the nucleus of hydrogen, the simplest, most abundant element in the universe. But also helium nuclei, carbon, nitrogen, iron, and occasionally something far heavier and far more energetic. When these particles reach Earth, they don't hit the ground directly. They slam into molecules in our upper atmosphere and shatter. The collision produces a cascade of secondary particles, an air shower that spreads across kilometers. This shower is what our detectors actually see. The energy in these particles is staggering. A single cosmic ray proton can carry the energy of a cricket ball hurled at 100 kilometers per hour. All packed into something 1,000,000,000 times smaller than a grain of sand. Now imagine particles carrying 1,000 times that energy, 1,000,000 times, a quadrillion electron volts. That is what we call a PeV, a peta electron volt, 1 quadrillion electron volts of energy. And whatever is producing cosmic rays at this energy, we call them p-vatrons. For comparison, the most powerful particle accelerator ever built by human beings is the Large Hadron Collider at CERN in Geneva. It can accelerate protons to about 14 tera electron volts, roughly 14 trillion electron volts. A pevitron produces energies 100 times higher than that. Whatever is creating these particles, it is operating at a scale of violence that has no parallel in human engineering. For decades, scientists have debated where cosmic rays come from. The problem is subtle and maddening. Because cosmic rays carry electric charge, they interact with magnetic fields, and our galaxy is threaded with magnetic fields. So by the time a cosmic ray reaches Earth, it has been bent and scattered so many times it no longer points back to its source. It's like trying to figure out where rain comes from by watching a single raindrop fall. But there is a loophole. When a pevitron accelerates particles, it doesn't just create cosmic rays. It also produces gamma-ray photons, packets of pure electromagnetic energy that travel in straight lines, completely unaffected by magnetic fields. These gamma rays are messengers. They carry a direct address pointing back to the source. And that is what astronomers have been hunting for. High in the mountains of Sichuan province in China, at an altitude of 4,400 meters above sea level, something extraordinary has been built. The Large High Altitude Air Shower Observatory, LHAASO. It is not a telescope, not a radio dish. It is something stranger and more magnificent, a field of detectors spread across 1.3 square kilometers, an area equivalent to 190 football fields. LHAASO consists of 3 interlocking systems. The first, 5,195 electromagnetic particle detectors, scintillating panels buried in the plateau designed to catch the particles in an air shower. The second, 1,188 underground muon detectors, tanks of water sealed beneath the Earth, waiting to catch the heavy particles that punch through the atmosphere. The third, the Water Cherenkov Detector Array, 78,000 tons of ultra-pure water held in 3,120 tanks. When a charged particle passes through water faster than light travels through it, it produces a cone of blue light called Cherenkov radiation. LHAASO sees this light. Together, these systems allow LHAASO to detect the highest energy particles in the universe with unprecedented precision. But why build it so high? At 4,400 meters, the air is already thin. The cosmic ray air showers that LHAASO studies begin in the upper atmosphere and they spread as they fall. By sitting this high, LHAASO catches them before they fully dissipate. The signal is stronger, the physics is clearer. In 2021, LHAASO published a result that sent shockwaves through the astrophysics community. It had detected gamma-ray photons from 12 different sources within our galaxy, photons with energies exceeding 1 peta-electron volt. 1 quadrillion electron volts from 12 different locations. Pevitrons confirmed. At last. Not quietly, not gently. In a catastrophic explosion visible across entire galaxies called a supernova. In a single second, a supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. Temperatures reach 100 billion degrees. The shockwave expands outward at 30,000 kilometers per second, 10% of the speed of light. What is left behind is called a supernova remnant, a vast, still expanding cloud of superhot gas and magnetic fields, the shattered corpse of a star. And this, many scientists believe, is where cosmic rays are born. The mechanism is called diffusive shock acceleration, sometimes called Fermi acceleration, after the physicist who first described it theoretically. Imagine a charged particle, a proton, near the expanding shockwave of a supernova. On one side, the hot, turbulent interior; on the other, the cold, quiet interstellar medium. The particle crosses from one side to the other. In doing so, it gains a small amount of energy, like a ping-pong ball, gaining speed each time it bounces between 2 approaching walls. It crosses back, it gains more energy, back and forth, over and over. Each crossing another boost, the particle accelerates and accelerates and accelerates. Given enough time and a powerful enough shock wave, particles can reach energies of 1 peta-electron volt and beyond. But there is a catch. The shock wave doesn't last forever. As the remnant expands and cools, the acceleration slows. Old supernova remnants, those that have been expanding for thousands of years, can no longer reach PeV energies. That means the PeVatrons we're looking for should be young, relatively fresh supernova remnants, still in the violent early phase of their expansion. Under 100 years old, finding young supernova remnants in our galaxy is no easy task. We are embedded in the Milky Way, surrounded by dust and gas that blocks our view in visible light. But not in gamma rays. Gamma rays punch through the dust. LHAASO, the Fermi Space Telescope, and HESS in Namibia have all been mapping the galaxy in gamma light, looking for the telltale signature of cosmic ray acceleration. Several candidate PeVatrons have been found. But proving that a supernova remnant is the source requires more than detecting gamma rays. Scientists need to show that the gamma rays are being produced by cosmic ray protons, not electrons, a distinction that requires careful spectral analysis. The hunt continues. Not every star dies the same way. When a star between 8 and 20 times the mass of our Sun explodes as a supernova, what's left isn't a black hole. It's something almost as strange. A neutron star, compressed to about 20 kilometers across, roughly the size of a city, but containing more mass than the Sunday. A teaspoon of neutron star material would weigh 1 billion tons on Earth. These neutron stars spin fast, absurdly fast. Some rotate hundreds of times every second, faster than a kitchen blender. And as they spin, they generate colossal magnetic fields trillions of times stronger than anything on Earth. When a neutron star's magnetic axis is tilted relative to its rotation axis, which is almost always the beams of radiation, it emits sweep across the sky like a lighthouse. We see regular pulses. We call these objects pulsars. But around some pulsars, something even more dramatic is happening. The spinning magnetic field acts like a generator, accelerating electrons and positrons outward at nearly the speed of light. These particles form a wind, a pulsar wind, that slams into the surrounding supernova remnant and creates a termination shock. At this termination shock, where the pulsar wind meets the resistance of the surrounding material, particles are catapulted to extreme energies. The question is whether these termination shocks can reach PeV energies. The math suggests they can under the right conditions. A young, rapidly spinning pulsar with a strong magnetic field, embedded in a dense remnant, might produce a termination shock powerful enough to generate PeV-scale gamma rays. There is one object in the sky that has become the cornerstone of pulsar astrophysics: the Crab Nebula. Messier 1. The Crab Nebula. A supernova remnant 6,500 light-years away, created by an explosion so bright that Chinese and Arab astronomers recorded it in the year 1054 AD. At its heart, a pulsar spinning 30 times per second. For decades, the Crab was considered the standard candle of high-energy astrophysics. Stable, well understood, a reference point. LHAASO shattered that assumption. In 2021, LHAASO detected gamma rays from the Crab Nebula at energies up to 1.1 peta-electron volts, the highest energy photons ever detected from this object. The Crab is confirmed as a leptonic pevatron, an accelerator of electrons and positrons, not a hadronic pevatron that accelerates protons, but still a landmark discovery. It tells us that pulsar wind nebulae can reach PeV energies. The hunt for hadronic PeVatrons, the kind that could explain the cosmic ray spectrum, continues with new urgency. There is a third candidate for the title of PeVatron, and it is perhaps the most dramatic of all. Black holes. When a star more than 20 times the mass of our Sun explodes as a supernova, the remaining core collapses past the neutron star stage entirely. Gravity wins completely. The core collapses to a singularity, a point of infinite density where our laws of physics break down. A black hole is born. In a binary system where a black hole orbits a companion star, material from the companion can fall toward the black hole. But it doesn't fall straight in. Conservation of angular momentum forces it to spiral, forming a glowing disk of superheated gas called an accretion disk. The temperatures in this disk can reach billions of degrees. The magnetic fields threading the disk become twisted and amplified. And particles, protons, electrons, can be slung outward along the magnetic field lines in the form of relativistic jets. But the most efficient acceleration might not happen in the jets at all. At the very edge of the black hole's event horizon, the point of no return, magnetic field lines can reconnect violently. This reconnection releases enormous energy, throwing particles outward at extreme velocities. Simulations suggest that under the right conditions, this process can accelerate protons to PV energies, making the region just outside a black hole's event horizon one of the most violent particle accelerators in the universe. The Cygnus region of our galaxy is one of the most active star-forming regions in the Milky Way. Dense clusters of massive stars, stellar winds slamming into each other at hundreds of kilometers per second. And at the center of it all, Cygnus X3. LHAASO detected gamma rays from this region at energies exceeding 10 peta-electron volts, potentially 10 times higher than previously confirmed PVatrons. If confirmed, Cygnus X3 would be in a category of its own, a super PVatron. But extraordinary claims require extraordinary evidence. The challenge now is to separate the contributions of different sources in this crowded region and build a complete picture of what is happening there. Understanding PVatrons is not just about finding exotic objects in the sky. It is about solving one of the deepest puzzles in all of physics, the cosmic ray energy spectrum. When you plot the number of cosmic rays arriving at Earth against their energy, you get a strikingly smooth curve, over 30 orders of magnitude in energy, an astonishing range. But the curve is not perfectly smooth. There are kinks. The first kink is called the knee, at around 3 to 5 peta-electron volts. Above this energy, cosmic rays become rarer, faster than the smooth power law predicts. What causes the knee? The leading explanation? At PV energies, cosmic rays begin to escape from our galaxy's magnetic field. Our galaxy can no longer contain them. The most energetic particles leak out into intergalactic space. But that raises a deeper question. What is accelerating them to the knee in the first place? This is exactly where PVatrons come in. If PVatrons are responsible for the cosmic rays at the knee, then finding and characterizing them would complete a picture a century in the making. From Victor Hess floating above Austria in a balloon to a detector array on a plateau in China, the entire story of cosmic ray physics has been leading here. But the plot thickens further. Above the knee, there's another feature, the ankle, at around 1 exa-electron volt, 10 million times higher energy than the knee. Below the ankle, galactic cosmic rays dominate. Above it, something changes. The chemical composition shifts. The particles appear to become lighter again. This suggests that above the ankle, we are no longer seeing particles from within the Milky Way at all. We are seeing cosmic rays from other galaxies, and whatever is producing those extragalactic cosmic rays, active galactic nuclei, gamma ray bursts, magnetars, they are operating at energies that dwarf even our galactic PVatrons. The universe, it turns out, has acceleration mechanisms at every scale, from the modest to the almost unimaginable. The results from LHAASO are just the beginning. Around the world, astronomers are building the next generation of instruments, each one designed to push deeper into the mystery of pevatrons. The Cherenkov Telescope Array, or CTA, will be the most powerful gamma-ray telescope ever built. With hundreds of dishes spanning 2 sites on 2 continents, it will have sensitivity 10 times greater than any current instrument and will be able to pinpoint pevatron sources with unprecedented angular resolution. IceCube, buried deep in the Antarctic ice, has already begun to detect high-energy neutrinos from the cosmos, ghostly particles that, like gamma rays, travel in straight lines and can point back to their sources. Future upgrades, IceCube Gen 2 will dramatically expand its sensitivity at PeV energies. Grand, the giant radio array for neutrino detection, would cover an area of 200,000 square kilometers in mountainous terrain. It aims to detect cosmic rays and neutrinos at the very highest energies, probing the extragalactic sources that may be responsible for cosmic rays above the ankle. The convergence of these instruments, gamma ray, neutrino, radio, and cosmic ray, represents a new era of multi-messenger astronomy. For the first time, we can cross-correlate signals from different physical processes and triangulate the identity of pevatron sources with real confidence. The mystery that Victor Hess uncovered from a balloon in 1912 may finally be solved within our lifetimes. We began this journey with an invisible storm, particles raining silently through your body as you watch this very video. And we have traveled far, to balloon flights above Vienna, to a Chinese plateau in the clouds, to the exploding hearts of dying stars, to the event horizons of black holes, to the edge of our galaxy and beyond. What is extraordinary about the search for pevatrons is not just the science. It is what the science reveals about the nature of the cosmos itself. The universe is not a calm, quiet place. It is a machine, a colossal, ancient machine producing energies at scales that make our most powerful technologies look like toys. And yet here we are, a species that emerged on one small rock around one ordinary star in one unremarkable corner of the Milky Way, and we are figuring it out. Balloon by balloon, detector by detector, gamma ray by gamma ray. The particles passing through you right now were born in the death of a star, perhaps thousands of light years away. They crossed the galaxy, bent and scattered by magnetic fields, surviving for millions of years to end their journey here, in this moment, in you. The universe is always speaking. LHAASO has given us ears to hear it. And what it is telling us is just beginning to be understood.